Hello there, and welcome to the Gentle Hours channel. I'm so glad you found your way here. Maybe tonight, your mind is restless, circling questions too big for the day to hold. Or maybe you're the kind of person who finds comfort in the deepest mysteries of all. Either way, you're in the right place. There's nothing you need to do now but rest. Let your breathing slow, your body soften, and your thoughts drift. Because tonight, we're journeying beyond the beginning itself, before stars, before galaxies, before even time as we know it. We're asking one of the oldest questions ever whispered into the void. What came before the Big Bang? Was there nothingness? Or something stranger still? We'll move gently from theory to theory, exploring ideas that stretch the imagination. Eternal universes, quantum foam, colliding brains, and the possibility that the question itself may not even make sense. Some of what you hear tonight may surprise you, challenge you, or simply drift through your mind like starlight. And if these calm explorations help you unwind, or spark your curiosity as you drift towards sleep, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The Big Bang might not have been the beginning. For most of the 20th century, the Big Bang was treated as the ultimate starting point. Time, space, matter, and energy all burst into existence from a singular moment of infinite density. But in recent decades, cosmologists have begun to wonder, what if the Big Bang wasn't the beginning at all, but just a transition? A phase change, like ice melting into water. Many theories now suggest that something existed before, not nothing. The Big Bang may have been the moment our universe became observable, but it might not have been the moment existence itself began. This shift changes everything. It turns the question from how did everything come from nothing into what came before and why did it change? Nothingness may be impossible. The idea of absolute nothingness is strangely hard to define. In physics, even a perfect vacuum, a space with no particles, no light, no matter, still contains something. Quantum fields permeate all of space, fluctuating constantly, creating and annihilating particle-antiparticle pairs in tiny, fleeting bursts. These fluctuations are real. They've been measured. They affect the behavior of atoms. So even when space seems empty, it hums with invisible activity. True nothingness, a state with no energy, no fields, no potential, may not just be unlikely, it may be impossible. Perhaps a universe in some form has always existed, not as stars or galaxies, but as potential, as process, as something waiting to unfold. Some theories propose the universe is eternal, cycling endlessly. One of the oldest alternatives to a singular beginning is the idea of a cyclic universe. In these models, the universe doesn't start once and expand forever. Instead, it goes through endless cycles of expansion and contraction. Each cycle ends in a big crunch, where everything collapses back into a dense, hot state. Then, instead of ending, the universe bounces, rebounding into a new Big Bang, a new expansion, a new cosmos. Each cycle might last trillions of years. The universe we inhabit could be just one chapter in an infinite story, with countless chapters before and countless still to come. Time doesn't begin. It loops, repeats, evolves. The past becomes a future, and the future becomes a past again. Quantum mechanics suggests the universe could emerge from nothing. In quantum theory, particles can appear and disappear spontaneously, borrowing energy from the vacuum for the briefest instant before vanishing again. This is called a quantum fluctuation. Some physicists, including figures like Lawrence Krauss and Stephen Hawking, have proposed that the entire universe could have emerged in a similar way. Not from absolute nothingness, but from a quantum vacuum, a state of minimum energy where the laws of physics still apply. In this view, the Big Bang was a quantum event, a fluctuation so large and energetic that it didn't collapse back into the vacuum. Instead, it expanded, cooled, and became everything we see. The universe, in a sense, is the ultimate something from almost nothing. Time itself may have begun with the Big Bang. One of the most radical ideas in cosmology is that time didn't exist before the Big Bang. According to general relativity, time is part of the fabric of space-time, woven together with space itself. If space-time began at the Big Bang, then there is no before.
The question, what came before the Big Bang, becomes meaningless, like asking, what's north of the North Pole? Time is a coordinate, a dimension, and if the universe began at a singularity, time did too. This doesn't mean something created the universe. It means the concept of causality, of before and after, only makes sense within the universe. Outside, or prior to it, those words lose their meaning. It's a strange and dizzying thought. Time is not a river we float on. It's part of the boat. The universe might have emerged from a multiverse. Imagine not one universe, but an infinite collection of them, each with different laws, different dimensions, different histories. This is the multiverse. In some versions of this theory, universes bud off from one another like branches on a tree or bubbles in an infinite foam. Our Big Bang could have been the birth of one bubble, a pocket universe inflating within a much larger multiverse. In this picture, there was no single beginning. The multiverse itself may be eternal, constantly generating new universes, each with its own Big Bang. We live in one branch of an endless cosmic forest. Before our Big Bang, there were other universes, other bangs, other beginnings. The question shifts from what came before to what surrounds us still. Inflation theory suggests a brief, explosive expansion just after the Big Bang. In the first fraction of a second after the Big Bang, the universe underwent a period of astonishingly rapid expansion called cosmic inflation. During this time, space itself stretched faster than the speed of light, smoothing out wrinkles and making the universe remarkably uniform. But what caused inflation? One idea is that it was driven by a quantum field, a kind of potential energy that filled space. When that field decayed, the energy was converted into particles and radiation, and the slower expansion we observe today began. Inflation doesn't explain what came before the Big Bang, but it does suggest that the early universe was governed by strange, powerful forces we're still trying to understand. It adds layers of mystery to the very first moments. Some propose the universe arose from colliding higher dimensional branes. In certain versions of string theory, our universe is a three-dimensional brane, a membrane floating in a higher dimensional space. Other branes may exist nearby, invisible to us because we're confined to our own. One speculative idea, called the ekpyrotic model, suggests that the Big Bang was caused by a collision between two branes. The impact released enormous energy, which became the hot, dense state we call the Big Bang. In this model, the branes may have collided many times before, and they may collide again. Time exists in the higher dimensional space, but within our brain, each collision feels like a new beginning. It's a cosmic crash, repeated across eternity, each one giving birth to a universe. Hawking proposed the universe has no boundary in time. Stephen Hawking, working with physicist James Hartle, developed an idea called the no-boundary proposal. Using a mathematical technique that treats time as if it were a dimension of space, they suggested that the universe is finite in time, but has no edge or beginning. Imagine the surface of a sphere. It's finite, but it has no boundary. You can travel around it forever without reaching an edge. In this model, asking what came before the Big Bang is like asking what's south of the South Pole. There's no before, because time, near the Big Bang, becomes smooth and curved, blending into space. The universe simply is. It has no starting point, no first moment. It exists as a self-contained whole. Loop quantum gravity suggests the Big Bang was a big bounce. Loop quantum gravity is an alternative to string theory, a way of understanding space and time at the smallest scales. In this framework, space is not continuous, but made of tiny, discrete units, like pixels in an image. When applied to cosmology, loop quantum gravity suggests that the universe couldn't have collapsed into a singularity of infinite density. Instead, quantum effects would have stopped the collapse and caused a rebound, a big bounce. In this picture, the Big Bang was not the beginning, but the turning point. Before it, there was a previous universe that had been contracting. When it reached a critical density, it bounced, expanding outward again to become our universe. The cycle could be endless, each bounce erasing most, but not all, traces of what came before. We may never be able to observe what came before. Even if there was something before the Big Bang, we may never be able to see it. The cosmic microwave background, the oldest light we can detect, was released 380,000 years after the Big Bang. Before that, the universe was opaque, a glowing fog that blocks light from traveling. And before the Big Bang itself, if such a time existed, any information would have been scrambled by the extreme conditions of the early universe. Quantum fluctuations, inflation, and the sheer violence of the Big Bang may have erased all evidence of what came before. We're left with theories, mathematics, and imagination. Some questions may never be answered by observation, only by reasoning, by inference, and by wonder. The universe could have been born from a white hole. Black holes are places where gravity is so strong that nothing, not even light, can escape. But the equations of general relativity also allow for white holes, the opposite. Regions from which matter and energy erupt outward, never to return. No white hole has ever been observed, and most physicists doubt they exist in our universe. But some have speculated that the Big Bang itself could have been a white hole. The interior of a black hole, seen from the outside, appears frozen in time. But from the inside, it might expand, creating a new spacetime, a new universe. In this view, every black hole might give birth to a new universe within its event horizon. And our Big Bang might have been the inside of a black hole from another universe, erupting outward into a space we call home. There might be no such thing as a true beginning. Philosophically and scientifically, the idea of a first cause is troubling. If the universe began, what caused it to begin? And what caused that cause? Some thinkers have suggested that the concept of a beginning is a limitation of human thought, not a feature of reality. Perhaps existence is simply fundamental, not created, not caused, just always present in some form. The universe, or multiverse, or quantum field, or whatever underlies everything, may have no origin story. It may simply be. This doesn't answer the question of what came before the Big Bang. It dissolves the question. There is no before. There is no beginning. There is only existence, shifting, changing, unfolding, but never truly starting. Some scientists think the Big Bang was a quantum tunneling event. In quantum mechanics, particles can pass through barriers they shouldn't classically be able to cross. This is called quantum tunneling. Some cosmologists have proposed that the universe itself tunneled from a state of nothingness, or near nothingness, into existence. In this model, the universe began in a quantum state with no time, no space, just pure potential. Then, like a particle tunneling through a wall, it transitioned into a classical universe with time, space, and matter. The Big Bang was the moment of tunneling, the instant when the quantum became the real. It's a strange, almost mystical idea, but it's grounded in the mathematics of quantum cosmology. The universe didn't explode into existence. It leaked through. The concept of before may require rethinking entirely. Our language is built for cause and effect, for sequences, for time flowing in one direction. But at the edges of physics, these assumptions break down. In quantum mechanics, particles can exist in superpositions, in multiple states at once. In relativity, time is relative, stretching and compressing depending on gravity and speed. Near the Big Bang, both quantum mechanics and relativity are essential, and they don't play well together. In this regime, the concept of before might not apply. Not because there was nothing, but because the structure of time itself was different. It may have been multidimensional, branching, probabilistic, or something we don't yet have words for. The question, what came before, may need to be replaced with something stranger, something we haven't yet learned to ask. Dark energy might hold clues to the universe's origin. Dark energy is the mysterious force causing the universe to expand faster and faster. It makes up about 68% of the universe's total energy, but we don't know what it is. Some theories suggest that dark energy is related to the same quantum fields that might have driven inflation in the early universe. If that's true, studying dark energy now could teach us about the conditions just after or even before the Big Bang. The energy that fills empty space today might be an echo of the energy that birthed the universe, a faint hum left over from the moment of creation, still shaping the cosmos billions of years later. The Big Bang singularity might not be real. In the standard model of cosmology, if you rewind time all the way back, the universe shrinks to a point of infinite density and temperature, a singularity. But singularities are troubling. They suggest a breakdown in our understanding, a place where the laws of physics no longer work. Many physicists believe the Big Bang singularity is not a real feature of the universe, but a signal that our theories are incomplete. Quantum gravity, a theory that successfully merges quantum mechanics and general relativity, might smooth out the singularity, replacing it with something finite and describable. If that's true, the Big Bang wasn't a point, but a region, a phase, a process. And processes have contexts. They have causes. They have befores. Information might have survived from a previous universe. In physics, information is never truly destroyed. Even when something falls into a black hole, the information about its state is preserved, though scrambled, in the radiation the black hole emits. If the universe went through a big bounce, collapsing and then expanding again, could information have survived the transition? Some models suggest yes. Subtle patterns in the cosmic microwave background or in the distribution of galaxies might carry faint imprints of a previous universe. These echoes would be hard to detect, buried in noise, stretched by expansion, but they might be there. Whispers from a universe that died so ours could be born. Some think the laws of physics themselves evolved. We tend to assume the laws of physics are eternal and unchanging. Gravity has always worked the way it works. Quantum mechanics has always been quantum. But what if the laws themselves emerged, evolved, or were selected? Physicist Lee Smolin has proposed a cosmological version of natural selection, where universes that produce black holes are more likely to spawn new universes, and the laws of physics are inherited and slightly mutated. In this framework, the laws we observe today might be the result of countless iterations, refined over deep time in a multiverse. Before our Big Bang, there might have been universes with different constants, different particles, different rules. The laws we live by are not eternal. They have a history. Asking what came before may be like asking what sound looks like. Sometimes a question can be grammatically correct, but conceptually confused. What does the color blue taste like? Makes sense as a sentence, but not as a question. Some physicists and philosophers argue that asking what came before the Big Bang is similar. If time is a property of the universe, not a container the universe sits inside, then before the Big Bang is a meaningless phrase. It's like asking what happened before time existed. The answer isn't nothing. The answer is that the question assumes a framework that doesn't apply. It's not that we don't know, it's that the question, as stated, may not correspond to anything real. The universe could be a simulation, and the Big Bang was the boot-up. In recent years, Some scientists and philosophers have entertained the idea that our universe might be a simulation, a computation running in some higher reality. If that's true, the Big Bang could have been the moment the simulation started. Before it, there was no universe, just code, potential, waiting to be executed. This idea is speculative, unfalsifiable, and deeply strange. But it's not absurd. If intelligence can create simulations, and if those simulations can become complex enough to contain conscious beings, then statistically, we might be more likely to live in a simulation than in base reality. The Big Bang, in this view, was not a physical event, but a logical one. The moment when existence was called into being by something or someone outside the system. Before the Big Bang, there might have been chaos. Some early models of cosmology, inspired by thermodynamics, suggested that the universe emerged from a state of maximum entropy, pure chaos. Over time, through random fluctuations, pockets of order appeared. One of those pockets became our universe. In this picture, the Big Bang was not the creation of order from nothing, but the emergence of temporary structure from an eternal, formless sea of chaos. Order is rare, fragile, and fleeting. Chaos is the default. And if that's true, then before the Big Bang, there was not silence or stillness, but an endless churning, a storm with no center, waiting for the right fluctuation to crystallize into a cosmos. We might live in a universe that is one of countless failed attempts. Imagine a process that generates universes randomly, each with different initial conditions, different constants, different laws. Most of them collapse immediately, fail to form atoms, or expand so fast that nothing can ever clump together. Only a tiny fraction of these universes are stable enough, interesting enough, to support complexity and life. We live in one of the rare successes. Before our Big Bang, there might have been countless attempts, countless universes that flickered into existence and died. We are not the first universe. We are one of the few that survived long enough to ask the question. The answer might be hiding in the mathematics. Cosmology is built on equations: general relativity, quantum field theory, thermodynamics. These mathematical structures describe the universe with stunning accuracy. But they also contain possibilities we haven't explored, solutions we haven't interpreted, symmetries we don't yet understand. Buried in the math, there might already be hints about what came before the Big Bang. Physicists are still working through the implications of theories like string theory, loop quantum gravity, and quantum cosmology. The answer might not require a new experiment or a new telescope. It might require a deeper understanding of the equations we already have. The universe speaks in mathematics. We're still learning to listen. The Big Bang might have been gentle, not violent. When we picture the Big Bang, we imagine an explosion, a violent eruption of energy. But that image might be wrong. The Big Bang was not an explosion in space, it was the expansion of space itself. And in many models, especially those involving inflation or quantum tunneling, the transition could have been smooth, gradual, almost serene, a quiet unfolding rather than a sudden blast. The universe didn't erupt, it exhaled. Before the Big Bang, there was tension, potential, a field balanced on a knife's edge. Then it tipped, and everything began to grow. Not with a bang, but with a breath. The question itself might change as we learn more. 1,000 years ago, people asked, "What holds the Earth up?" Today, we know the question is based on a misunderstanding of gravity and motion. The question dissolved. In the same way, our question about what came before the Big Bang might one day seem quaint or confused. Future physicists, with better theories and deeper insights, might look back and smile, not because they have the answer, but because they've realized the question was never quite right. The mystery won't vanish. It will transform into something richer, stranger, and closer to the truth. Every culture has grappled with the question of origins. Long before the Big Bang Theory, humans looked at the night sky and asked how it all began. Ancient myths spoke of cosmic eggs, primordial waters, gods shaping clay into form. Some traditions described creation as a spoken word, a thought made real. Others imagined an eternal cycle with no true beginning or end. These weren't just stories, they were humanity's first attempts to make sense of existence itself. And while modern cosmology uses telescopes and equations instead of mythology, the question remains the same. Where did all this come from? The tools have changed, the wonder has not. Some physicists believe the Big Bang was just a local event. What if the Big Bang didn't create the entire universe, but only our observable part of it? In eternal inflation theory, the universe as a whole is constantly inflating, expanding exponentially. But within this vast inflating space, small regions occasionally stop inflating and undergo a Big Bang, creating pocket universes like ours. Each pocket has its own physics, its own constants, its own history. From our perspective, the Big Bang looks like the beginning of everything. But from a larger view, it was just one bubble forming in an infinite cosmic ocean. Before our Big Bang, there were other bubbles, other bangs, other regions blossoming into existence. We are one island in an infinite sea. The concept of entropy might explain why there was a Big Bang at all. Entropy is a measure of disorder, of how spread out and randomized energy becomes over time. The second law of thermodynamics says that entropy always increases. But here's the puzzle. The Big Bang began in a state of incredibly low entropy, highly ordered, compact, and dense. How did the universe start in such an unlikely, ordered state? Some physicists propose that the answer lies in gravity. Gravity is strange because it can create order by pulling things together, lowering entropy locally, even as the universe as a whole becomes more disordered. Perhaps the conditions before the Big Bang naturally led to a state where gravity could take over, condensing energy into a dense, low-entropy seed. And from that seed, the universe exploded outward, not randomly, but with structure already encoded in its beginning. Space and time might be emergent, not fundamental. We think of space and time as the stage on which everything happens. But what if they're not fundamental? What if they emerge from something deeper, something more basic that we don't yet understand? Some theories in quantum gravity suggest that space and time are not the bedrock of reality, but patterns that arise from interactions of more fundamental entities, like information or quantum entanglement. If that's true, then asking what came before the Big Bang is like asking what comes before the pattern in a kaleidoscope. The pattern emerges when the pieces arrange in a certain way. Before the arrangement, there is no pattern. Before the conditions that give rise to space-time, there may be no before at all. Reality itself might be an emergent phenomenon, a layer of meaning built on a foundation we can't yet perceive. The universe might be a hologram, and the Big Bang a projection. Holographic principle is one of the strangest ideas in theoretical physics. It suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram on a two-dimensional surface. Applied to cosmology, this means the entire universe, including the Big Bang, might be a kind of projection, a three-dimensional image encoded in information on a distant boundary. In this view, the Big Bang wasn't a physical explosion, but the beginning of a projection, the moment when information on the boundary started to unfold into the illusion of space, time, and matter. What came before? Perhaps just the boundary, timeless and unchanging, waiting for the projection to begin. The anthropic principle suggests we exist because the universe allows us to. The anthropic principle is simple but profound. We observe a universe that supports life because if it didn't, we wouldn't be here to observe it. This doesn't explain why the universe is the way it is, but it does explain why we find ourselves in a universe with the right conditions. If there are countless universes, each with different properties, most would be lifeless, sterile, and uninteresting. We, by definition, must find ourselves in one of the rare ones that allows complexity and consciousness. This principle can be applied to the question of what came before. If many processes, many bangs, many attempts occurred, we exist in the outcome that succeeded. The universe before our Big Bang might have tried and failed countless times. We are the descendants of the attempt that worked. Vacuum decay could have triggered the Big Bang. In quantum field theory, empty space isn't truly empty. It's filled with fields that can exist in different energy states. Our universe's vacuum might not be in the lowest possible energy state. It might be in a metastable state, like a ball resting in a shallow dip on a hill. If the vacuum decayed, dropping to a lower energy state, it would release enormous amounts of energy. Some physicists have speculated that the Big Bang could have been triggered by a vacuum decay event, a transition from one vacuum state to another. Before the Big Bang, the universe might have been in a different vacuum, stable and quiet. Then, a quantum fluctuation nudged it over the edge, and the decay released the energy that became our universe. A cosmic phase transition, sudden and irreversible. We might be living in the exhale of a cosmic breath. Imagine the universe as a living system, not conscious but dynamic, breathing in and out across unimaginable timescales. The Big Bang could be the exhale, the expansion, the outward rush. Before it, there might have been an inhale, a contraction, a gathering of energy and matter into a dense core. And before that, another exhale, another universe. This isn't a scientific model exactly. It's a metaphor, a way of thinking about cycles and rhythms on a cosmic scale. But it captures something essential. The universe is not static. It moves, it changes, it pulses. And what we call the Big Bang might be just one beat in a rhythm that has no beginning and no end. Some propose that consciousness itself might play a role in creation. This is the most speculative, most controversial idea of all. A few physicists and philosophers, influenced by quantum mechanics and the measurement problem, have wondered if consciousness plays a role in collapsing quantum possibilities into reality. If that's true, could consciousness in some form have played a role in the Big Bang? Not human consciousness, but something more fundamental, an observer embedded in the structure of the universe itself. This idea is not mainstream. It's not testable, but it's an echo of ancient questions. Does the universe need to be observed to exist? If a tree falls in a forest and no one hears it, does it make a sound? And if a universe begins and no one is there to witness it, did it truly begin? The Big Bang might have been one quantum fluctuation among infinite others. In the many worlds interpretation of quantum mechanics, every quantum event spawns multiple outcomes, each occurring in a separate branch of reality. Applied to cosmology, this suggests that the Big Bang might have been one quantum fluctuation among infinite others, each creating a different universe. Before the Big Bang, there was a quantum state, a superposition of all possibilities. And in that superposition, countless Big Bangs occurred, each one real, each one creating a different branch of the multiverse. We live in one branch, but the others are equally real, unfolding in parallel, invisible to us. The question, what came before, becomes, what else is happening now in all the other branches we can never see? The speed of light might have been different in the early universe. One of the constants of physics is the speed of light. But what if it wasn't always constant? Some alternative cosmological models propose that the speed of light was much faster in the earliest moments after the Big Bang, then slowed to the value we measure today. This idea, called variable speed of light cosmology, could solve some of the same problems that inflation solves, like why distant parts of the universe look so similar. If light traveled faster back then, those regions could have been in contact, exchanging energy and information before settling into the structure we see now. If the speed of light can change, what other constants might have been different before or during the Big Bang? Perhaps the universe's fundamental rules are not as fixed as we think. We are made of questions as much as matter. Your body is made of atoms. Those atoms are made of particles. Those particles emerged from the energy of the Big Bang. But you are also made of something else. Curiosity, wonder, the need to ask why. These aren't physical things, but they're real. They shape your thoughts, your actions, your understanding of the world. The question of what came before the Big Bang is part of you, just as much as the carbon and oxygen in your cells. And that question, that need to know, that refusal to accept mystery without exploration, is itself a kind of answer. It says that the universe is not just matter and energy. It's also meaning, inquiry, and the search for truth. You are the universe asking itself where it came from. Time might be an illusion we experience because of entropy. Physicist Carlo Rovelli has proposed that time, as we experience it, is not fundamental, but emerges from the increase of entropy. In a universe at maximum entropy, perfectly disordered and uniform, there would be no sense of past, present, or future. Everything would be static. But in a universe with low entropy, like the one we inhabit, there's a direction, a flow, an arrow of time pointing from order toward disorder. This is why we remember the past, but not the future. Why eggs break, but don't unbreak. Why we age and stars burn out. If time is an emergent property of entropy, then before the Big Bang, when entropy was at its lowest, time might not have existed as we understand it. The question, what came before, assumes time flows backward infinitely. But if time itself is emergent, the question falls apart at the edges. The universe might be fine-tuned, or we might just be lucky. The constants of physics, the masses of particles, the strength of forces, all seem remarkably well-tuned to allow life. Change any one of them by a tiny amount, and stars wouldn't form, atoms wouldn't be stable, chemistry would collapse. Some see this as evidence of design, a multiverse, or some selection process. Others say it's just luck. We exist, so of course we find ourselves in a universe where existence is possible.
But this fine-tuning might hold clues about what came before. If the constants were set during the Big Bang, or just before it, then understanding why they have the values they do could reveal something about the initial conditions. Was the universe born with intention, with randomness, with a process that selects for stability? The fine-tuning is a clue. We just don't yet know what it points to. There might be no ultimate answer, and that's okay. Science is often framed as a quest for answers, but it's also a quest for better questions, for deeper understanding, for models that fit the data and make predictions. We may never know with certainty what came before the Big Bang. We may never observe it, test it, or prove it. But that doesn't make the question worthless. Every attempt to answer it sharpens our thinking, refines our theories, and expands our imagination. The journey matters as much as the destination, maybe more, because the journey is where we live, where we discover, where we grow. The universe may keep its secrets, but in trying to uncover them, we become more than we were. More curious, more humble, more alive to the mystery that holds us. Science thrives on unanswered questions. It's easy to feel frustrated by all the uncertainty, by the theories that contradict each other, the models that can't be tested, the questions that seem unanswerable. But this is where science lives. Not in certainty, but in the tension between what we know and what we wonder. Every question we can't yet answer is an invitation to think harder, to imagine bolder, to look deeper. The question of what came before the Big Bang is one of the greatest questions we've ever asked. And the fact that we're still asking it, still refining it, still exploring it, is a sign of how far we've come and how much further we can go. And now, let the edges of thought begin to soften. We've wandered through singularities and cycles, branes and bounces, quantum foam and white holes. We've asked what came before and found not one answer, but many. Some contradictory, some complementary, some strange beyond imagining. You've heard of universes born from collisions, from fluctuations, from the decay of fields we can't even see. You've considered the possibility that time itself might be a late arrival, that nothingness might be impossible, that the Big Bang was not the beginning, but a transition. And through it all, a quiet truth remains. We don't know. Not yet. Maybe not ever. But the not knowing is not emptiness. It's possibility. It's wonder. It's the space where imagination and mathematics meet, where curiosity becomes discovery, where questions become quests. You are part of this story too, not just as a listener, but as a being made of the very matter that emerged from whatever came before. The atoms in your body were forged in stars, yes, but those stars came from galaxies, and those galaxies from the cooling remnants of the Big Bang. And the Big Bang came from something. We don't know what, but you carry it with you, in your breath, in your bones, in the electrical sparks that let you think and dream. You are a continuation of the universe's deepest mystery, a question asking itself what came before. So wherever you are now, let yourself rest.
Let the questions drift like clouds. Let your breathing slow to the rhythm of the cosmos itself, vast and patient and endlessly unfolding. The universe began, or it didn't. Time started, or it never stopped. Something came before, or the question dissolves in the math. It doesn't matter tonight. What matters is that you are here, now, alive in a universe that is real enough to hold you. And that is its own kind of miracle. If you happen to still be awake, you can go ahead and watch the next chapter now. And if you'd like to drift off to more stories like this, softly told and filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Sleep well, and thank you for dreaming with us. Good night.